Hi you all, how are you doing? This is Celso Batalha, and today I will be focusing on terrestrial worlds, which is a continuation of what we saw before as far as star formation process is concerned. So the assignment this day or today, the assignment is you're gonna answer multiple choice questions that I will ask during this taping lecture. And so there will be 5 multiple choice questions you have to answer. So you have to, my recommendation is get a piece of paper, and as we go through the taping, through the video, just answer or write your answers as we go, and then you upload and turn it in. Is that a good deal? Before I start, let me show you something here. There is an extra credit, and I hope you can see um, this. There is an extra credit on today. Yeah, it's called Star Formation, Star Death. You click on it, and let me call your attention to something here because I like this video. In fact, it's very good, but there is a problem with it. So right in the beginning, it shows the formation of our solar system after a big bang. Boom! You know, don't fall for that. It's a wrong depiction of what goes on star formation. Star formation, as we saw last week, is a process by which gas that happen to be spread over a very large volume gets pulled in by gravity. So we start very cold, in fact super cold, super thin. The gas is very thin, very cold, and gravity pulls in, and then it slowly and constantly, and take, let's say, for the sun 20 million years for that contraction to lead to a system that has a star and planets. So it doesn't happen with a boom like people usually think with respect to the Big Bang. So Big Bang theory is a theory that explains how the universe started. So it's a very condensed, infinitely condensed state of matter, very high temperature, and a sudden expansion brings um, a constant and steady cooling process by which eventually conditions are such that atoms start to be formed, and then a few hundreds of millions of years later, then the recombination takes place, and then another step, and then boom, we have stars. So um, just look at this video, and I like to show because there are very cool things in there. See, this is a bad idea. So right there is a bad idea, right? So don't think about formation of the solar system like a big boom, and then that is the stars and planets. So it doesn't go that way. Yeah. So this cloud you just saw passing by are regions where stars are formed. Okay, like those ones. There you go. That's the giant molecular clouds, and eventually contraction will lead to core formations of several cores. Here and there, each one birthplace of the future star. That's Professor Gibor Basri. He's a professor at UC Berkeley. Okay, so let's go to our slide number 1. And terrestrial words. Can I spin this further? I don't think I can. Can I? Let's see. Oh, I cannot. There you go. That's the most I can expand. Okay, terrestrial words. So terrestrial means words that resemble terra. Terra is a Latin name of our planet Earth. Earth, terra. So which means objects that have solid surface. So solid surface implies that if something falls on it, it's going to create craters, right? Craters. You do not expect to find the craters in the Jovian planets, in the giant gas or liquid type planets such as Jupiter, Saturn, Uranus, and Neptune. You might find in their moons, because their moons have solid surface, but not on the planets, the Jovian planets themselves, because their surface is pretty much gas. Okay, so which terrestrial worlds are there? Mercury, Venus, Earth, Mars. Don't forget the satellites. Earth has a satellite, Moon. Mars has two satellites, Phobos and Deimos. Mercury and Venus have no satellites. But those are terrestrial worlds. Another one is asteroids. Asteroids, a bunch of planetesimals that are left over from our solar system formation, and they still exist in between the orbits of Mars and Jupiter. They are also terrestrial worlds. They are made of rocket type material. Okay, here is our first multiple choice questions. How would you rank the size of these terrestrial planets from the smallest to the biggest? What's the answer? Answer number 1, 2, and 3. Well, if you look at this table, do I have a table? I think I have a table. Yeah, I do have a table. Look at this. This table shows the size, equatorial radius. Um, so the equatorial radius, this is in respect to Earth, right? No, it's not in respect to Earth. This is in kilometers. It is in kilometers. So this shows that Mercury has 2,400 kilometers. 2,400 kilometers. So Earth has a radius, so the average distance from the center to the surface, of about 6,378 kilometers. So if you want to convert that to miles, multiply that by 0.6, so it's about 3.6, 3.7, 3,700 miles um, Earth radius. So which one is bigger? Which one is smaller? You can look at this table here and have some good idea. Of course, Moon is also terrestrial world, but Moon is not a planet. So then you can answer what is the in order of increasing planetary radius. Which one is the biggest? Which one is not? Okay, you can stop um, and try to answer here, but it's right there. The answer is in the table. Okay, cool. Let's keep moving. Oh, what is this? How does the solar nebula theory accounts for the drastic? Okay, this I think I covered last in last tape, the one you might have probably watched yesterday. Um, this is not one of the questions I would like you to answer, but let's go through that. What's the difference between terrestrial and Jovian planets? Well, remember the solar system and the star systems form in such a way there is a hot central star surrounded by a circumstellar disk, and the inner regions of the disk happen to be exposed to a higher heat, the heat that comes from the star itself. In addition, there are some viscosity forces, there are something going on in the disk and make it hotter in the inner regions, hotter than it is in the outer regions of this disk. So, which means terrestrial planets, those closer to the sun, will not have volatiles, will not have ices because the region is too hot, right? So they will have metal oxides, they will have silicates, but they will be rocky type. As opposed to the Jovians, they will have more of a volatile content. They also have rocky material in their center part, but it's going to be more volatiles than anything else. So let's go through the answers. The temperature of the accretion disk was high close to the sun and low far from the sun. Um, this is true. This is true. But the major difference is it has to do with the condensation of different types of materials. Terrestrial planets formed closer to the sun and are thus made of high density rock type. This is true too. Yeah, this is true too. So number one is true. I mean, the disk is hotter closer to the star than it is in the outer skirt, and the second one seems to be good too. Number three, Jovian planets are large and have high mass because they formed where both rocky and ice material can condense. This is true too. Don't forget Jovian planets, these guys, these giant-like planets, they have the rocky material because eventually the temperature passed through the phase where dust grains can be formed, but it kept on going low to the point of allowing ices to be formed. So number three seems to be good. Number four, Jovian planets capture nebular glass, and that's true. So once planetesimals in the Jovian regions clustered to form protoplanets, since the region was also populated by gas, this gas just keep on falling and falling and falling. These planets grew to be very large. So the proper answer, I think, would be number five for that one. But don't email me answer. I don't want to answer for that. So Jovian planets, like terrestrial planets, they do have craters. This kind of things you're seeing. This looks like the Behringer crater in Arizona. Is a great place to go if you have some free time. Go to this Behringer crater. Visit there. So you park somewhere here, and then you walk around, and then you can see. You still have um, some leftover that the Behringer, the guy who got this crater in the beginning of 20th century. He thought he was going to find lots of metals and to be used in in the construction of the railroads. He didn't find that, but you have a craters, you can go there and enjoy yourself. But our planet Earth has tectonism. What the heck is tectonism? Tectonism means our planet Earth, the solid surface, is divided in 12 or more major plates. Like imagine, it's not true what I'm going to say, but imagine, just for the sake of imagination, you have a kind of a floppy or liquid. It's not liquid, but it's kind of a plastic mantle that is covered by plates, and these plates can move on this kind of a fluid mantle, and because there is some motion, and the motion is very small. I mean, it's few centimeters per year, few a third or so of an inch per year. So it's not so fast, but that is enough to allow these plates collide in large scale, or pass one another, or diverge from one another. And this motion is called plate tectonic or tectonism, that give rise to most of the activities we witness on Earth, like volcanoes, like earthquakes, and hotspots, and things like that. Okay, so smaller terrestrial objects don't have that because they might have been completely cooled to the point everything is brittle, and you don't have plate motion anymore. Planet Earth, of the terrestrial objects, is the only one is still with enough activity, geological activity, enabling plate tectonics. So plate tectonics is responsible for, in a process we call subduction, to eliminate most of the surface that existed since billions of years ago, 3 billion years ago, which means we don't have a lot of a crater exposed anymore because most of it have gone um, um, under this, um, have disappeared under this process we call subduction. And I think I might have some picture in the further down to show. And another process that explain why we don't have a lot of craters visible on Earth. I mean, Beringer is one of the few examples of craters we we have. We don't have a lot. Like in the Moon, we have tons of it. Is because we have erosion. We have an atmosphere, and the atmosphere recycle the topography, the surface of our planet is washed out by the hydrological cycle. Okay, and also we have volcanoes, all kind of things. So, but primarily erosion. So planets, if the planets are too small, they don't have enough gravity. Remember gravity? They don't have enough gravity to hold on to an atmosphere. So the atmosphere go away. Like Mercury doesn't have an atmosphere. Mars has a very thin atmosphere. Venus and Earth, somewhat bigger, they have atmospheres. But Mars has a very thin one, 1/100th of ours, as far as density is concerned, and Mercury has no atmosphere; it lost, and these lighter gas were pushed out to the regions where the Jovian planets happen to be located. So bigger terrestrial planets have better chances of hold on to an atmosphere. Bigger, massive terrestrial planets have better chance of having tectonism because they are still active. Okay. And here's some nice examples of craters. This looks like a crater in Mars. Looks like a crater in Mars glowing. See this impact here? It's kind of a sharp, right? Which means it's somewhat recent. But you see this splatter? Looks like a mud splat as a result of impact. Mars has a subsoil that is frozen and has liquid, in fact, ice water and carbon dioxide. But this impact gives enough heat to create this mud splatter, as we call. Okay. This is more cratering. It looks like the moon. This thing. Yeah. Now, this is a question I would like you to answer and send me the answer either A, B, or C. Imagine take a picture of the moon about 2 billion years ago. What would you expect to see? What's the point of this question? Well, because most of the craters formed in our solar system happened in the very early moments of our solar system, in the infants of our solar system, where several planetesimals and all kind of material that were building up and growing up in planetesimals that later on coalesced into protoplanets. So these planetesimals were falling on protoplanets once their surface got sufficiently brittle and hard, creating these impact craters. So the era of bombardment happened in few hundreds of millions of years after most of the terrestrial planets got hard and solid surface. So which means in from let's say 4.2, 4.3 billion years ago up to about 3.8, 3.6 billion years ago, most of the impact happened, and after that the rate in which this impact happened decreased a lot, to the point that this is the point of this question. So if you take a picture just 2 billion years ago and now, you are not going to see a lot of differences. Most of the major impacts that happen on the moon surface happen in earlier days than 3.5 billion years ago, like the big muddies and all of them. Okay. So this is the second multiple choice question. You should upload your answer through Turnitin. Just put A, B, or C. You don't need to say much, right? I understand you got it. Um, let's say this. I would that's a good one. That would be nice if you also send me an answer to this question number three. You discover an Earth-like planet around another star, but the planet has twice the mass of Earth. What would you not expect to see? That's a tough one, huh? But just think about it. If you have a smaller terrestrial planet, gravity will not be strong enough to hold on to an atmosphere, right? So if you have a bigger, more massive planet, chances are these terrestrial planets will be more efficiently to hold on to an atmosphere, right? So if you have an atmosphere, what do you have? Well, if it's terrestrial, if it's in a habitable zone where you can have liquid water, you might have a nice chance of having hydrological cycle, erosion, tectonic motions, so craters will be raised and things like that. Can you answer your question now? Um, this is simple. Don't worry about this. Where are most asteroids located? Of course, between the orbits of Mars and Jupiter. You don't need to answer that one. So every time there is an earthquake, seismic waves travel through Earth interior, through the mantle and the core. Remember, Earth is divided in a solid inner core, an outer liquid core, and a mantle. So the mantle is not liquid, it's solid, but it's plastic. It can move, it has motion in it. But there are seismic waves are the waves by which we can create a profile of Earth interior. We know what Earth interior is divided. I mean, the regions Earth is our interior is divided is pretty much mapped by seismic waves. Like P waves, the primary waves can go through solid and liquid phase, but S waves, the shear waves, doesn't go through the liquid phase; it rebounds. So there is shadowy regions where shear waves, secondary waves, don't show up. If you have seismic stations exactly in opposite direction on Earth as where the epicenter happened, because secondary waves don't go through the liquid phase. That's how we know Earth interior is made of. Um, how about this? This I would like you to answer this question. That's question number 4. Which of the following accurately describes the differentiation process? What's differentiation? Chemical differentiation is. So chemical differentiation is the process by which heavier, denser material sinks to the core, sinks to the center. I saw a good example. You take a bucket of ice cream. Oh, I'm getting hungry now. A bucket of ice cream, chocolate chips ice cream. Vanilla with chocolate chips. That one. It's very good. So imagine you have chocolate chips everywhere in your ice cream bucket, and then you go to your store and then you get a bucket of that, and then you're dreaming at home and start eating that. But then what happened when you park your car? Your nice neighbor come talk to you, and is one of these neighbors that never give up. I mean, you try just to wait for the moment that you can step in and say something, say, hey, dude, you know, just, just get a life. But you can't because the guy never stopped talking. And as it happened quite often in the summer, your ice cream get all melted. So what happened with the chocolate chip? It's gonna sink to the bottom of the bucket, right? So in Earth, if you think about a proto-Earth, a long time ago, it was entirely liquid because of radioactive process liberated by unstable atoms in the planet interior who melt down the entire planet. And the same happened. So we have to have a situation where the planet or the object you're studying, like an asteroid like Vesta, is entirely liquid. And then the heavier atoms sink to the core, and the lighter atoms or minerals or molecules stays on top, and the even lighter stays above in the atmosphere. So chemical differentiation is this. When we say that a body in the solar system is differentiated, it means that it has a core of solid iron, which is heavy, surrounded by a mantle of some silicates, lighter silicates, and lithosphere that is even lighter, and an atmosphere above. So that is what's called differentiation. Okay. So you can answer this question. It's a good depiction of how the moon was formed, collision of Earth or proto-Earth by a proto um, uh, planet, and there are a couple of different names given in the literature to this colliding object, and I think one of the extra credits are based on that. I ask you to watch a video and I ask questions about it. Okay. Now I think we are approaching our last question, but don't worry about this. Let's keep moving. Tides. Um, According to Newton's third law, an object that has mass exerts an attractive force to an object that has mass with an intensity that depends on the mass, the product of the mass of these two objects divided by the square of the distance. So which means a moon attracts Earth, Earth attracts the moon. If since Earth has a water surface, it's easier to see this water bulging up towards the moon, as here. See that? So Earth should be completely stable, but it is stable. But the moon pulls the water towards it. But Earth also rotates, right? It has a rotation. So Earth takes this bulging water a little bit off the line connecting Earth itself and the moon. So the bulging region stays always a few degrees above the line connecting center of Earth and center of the moon. But the bulging is caused by moon's gravitational pull on Earth. Okay, and which means as Earth rotates, little rocky material cliffs that encounter this bulging water causes some friction, and then energy or momentum, angular momentum or rotational um, energy is lost in that process and transferred to the moon. The moon goes a little bit away from Earth as every year, and I think you might have read that in your textbook. So that's the idea of the tides. I think we are pretty much finishing it. Don't worry about this question. Look at this moon. See all these little edges here? This is indication of lava flow that happened in the moon a long time ago in the regions called Mare. And I guess that's it. Oh, yeah, answer this question. This is the fifth question, the last one. This last one. What should be true about Earth's interior heat? A. It is produced by magnetic field. Yeah, don't worry about it. In fact, magnetic field is produced on Earth because Earth has a melted core and rotates, and that ionic motion generates a global magnetic field. So the magnetic field exists because Earth has a hot interior, not the other way out. So A is not a good answer. See, I'm giving you the answers. B, it would have been greater long ago when Earth was young. Could be. I mean, a long time ago, Earth was um, younger and hotter, right? Remember, Earth a long time ago was entirely liquid, which means it was entirely um, temperature was internally larger than it is now because differentiation occurs on Earth. We need to have the planet or the object completely liquid. Remember that? It currently is produced by differentiation. Yeah, no. I mean, the heat, you have some heat still existing from the moment. Like if you bake a potato and you take the potato and leave it out, the heat slowly goes away, but you still have some from the moment the potato itself was cooked. Same thing on Earth. So we still have some heat that exists because Earth was formed a long time ago and was hotter than it is now, so you have some heat still there. But primarily source of heat, internal heat, is radioactive decay that keeps Earth hot as it is. So to the point that smaller planets like Mercury don't have that many um, unstable atoms, and the internal heat might not be there anymore, or it might. We have to measure that. Okay, that's it. 5 questions. Thank you.